Hello and welcome to our presentation about VIME, Variational Information Maximizing Exploration. A long-standing problem in reinforcement learning is how to manage the trade-off between exploration and exploitation. In exploration, the agent experiments with strategies that may improve returns in the long run. And in exploitation, it maximizes the rewards through behavior that is known to be successful or good. Commonly, simple heuristics are used to achieve this, but they often rely on random walk behavior. For tasks with sparse rewards and especially continuous control, these methods are not really feasible since they can be highly inefficient. An example for this problem would be, for instance, the mountain car or the walker 2D. As a solution for such problems, this paper proposes a curiosity-driven exploration strategy, which is based on the concepts of curiosity and surprise. Hereby, the agent engages in systematic exploration by seeking out state action regions that are relatively unexplored, and thus resulting in surprising states for the agent.
So let's get some intuition on how VIME is this and get some preliminaries out of the way. First, in VIME, the agent models the environment dynamics using a model which is parameterized by a random variable big theta with values small theta. We are also given the agent history, and our goal is to plan for maximum expected information gain, meaning we want to reduce the uncertainty in the model dynamics. In other words, we want to plan to be surprised. VIME does this by adapting the reward function. This new adapted reward function can be seen here. Don't be scared off. We get to every part of it. First, VIME adds information gain to the original reward. This information gain can be seen as how surprising the next state will be for the action the agent takes. To be more precise, this information gain can be expressed as the difference between the distribution over the model parameters given the current trajectory and the distribution over the model parameters given the current trajectory and the next state action pair. Additionally, we have a hyperparameter called eta, which represents the urge to explore. It basically weights the information gain term and can therefore be seen as controlling the trade-off between exploration. However, we have a problem. The posterior used in the Kuiper-Kleibert divergence is in general intractable. So to get around this problem, VIME approximates this information gain term using an alternative distribution in a process called variational inference. For reasons of simplicity, however, we'll not go further into detail since this would exceed the scope of this presentation. We will now show you experimental results of VIME in different settings.
First, let's look at a task with sparse rewards. Here we have a look at the trusty old mountain car. As we can see, the performance of a common reinforcement learning algorithm, in this case TRPO, which is Trust Region Policy Optimization, performs way better and converges quicker with VIME than without. Furthermore, on the right, you can see the vastly greater exploration of the state space when VIME is utilized versus a smaller region in blue in the middle without VIME. Next, we can have a look at a more challenging hierarchical task, that is the swimmer-gather task. Here also TRPO is used with and without VIME, and as one can clearly see, the algorithm with VIME outperforms the baseline model greatly, to the point where TRPO doesn't manage to solve the task at all. Finally, we return back to the mountain car example to compare different reinforcement learning algorithms utilizing VIME. One can clearly see that episodic reward weighted regression is no match in this task for its VIME counterpart. where the baseline barely manages to gain rewards at all. Reinforce, on the other hand, manages to solve the task fairly well. However, Reinforce with VIME again outperforms the baseline by the time it takes to converge and how quickly reward is acquired.
In summary, we discussed VIME and how by means of curiosity-driven exploration, it outperforms other methods based on heuristics. The idea of curiosity-driven exploration is fairly intuitive and in principle is a simple one. Yet, we can see significant results. Note that, however, we merely gave a high-level introduction to VIME. For deeper understanding and implementation details, we refer to the paper itself. There you can also find a discussion on how VIME and the techniques of VIME relate to compression improvement and how Bayesian neural networks, BNNs, are used throughout VIME.
Thank you for bearing with us.